about Dapper. First time? Okay, cool. So my name is André Freitas. I work here at Talkdesk at the data platform team. I do essentially backend. And I started reading this paper 2 years ago when I was at André, and we were having some over latency in a single endpoint. It was a critical endpoint for our application, and I read this paper because I've used Zipkin that implements the knowledge from this paper. So it's very interesting, and I read again in the reading group that Pedro presented. So doing a deep dive in the paper, I found it more interesting than 2 years ago. So I challenged Pedro, can I do a talk in the PapersWeLove? Let's start in January, that's why I am here. Okay, so here, can you hear my voice perfectly? Those guys with the laptops, okay, cool. So the paper is from 2010, 9 years, right? The time has passed. I will follow you the same sections of the paper. I just pick topics that are relevant for the audience we have here. I left some topics on the end that I'm not going to mention, but it's the more important for the context we have right now. Okay, so first of all, the problem that we are talking here is about tracing. So imagine that you are searching at Google. That search triggers a lot of requests in service A, B, C, and D, and you observe a global latency. You may ask, what is the server that is causing this latency? That's why tracing is important. Tracing gives you information about the time taken in every service you have for that request in specific. And Google had this challenge. And they wanted to design a tool called Dapper with 3 design goals: being low overhead, being transparent in the applications, don't require a lot of code changes, and be ubiquitous. Don't require a lot of effort in infrastructure for every time a new application is deployed. And the motivation is, as I said, even for experienced developers, when you have a complex microservices infrastructure, you don't know, like this, what is the source of the problem, what is the source of latency. You need tools, you need ways of finding stack traces in production that can help you diagnose the bottleneck. And you know, Google is big. They have a lot of service. Detailing on the requirements of Dapper, first of all, is having low impact. This actually happened here at Talkdesk. We are using New Relic for instrumentation, and we switched it off because the implementation we did in Elixir was not performant. So we find the bottleneck that was the instrumentation part of New Relic in Elixir, and we switch it off. Okay, so this requirement is very important. The teams will switch it off if there is performance impact. So application transparency, another important requirement. If you want to implement tracing in every service of your company, if you ask teams, hey, you need to change a lot of code, they will not prioritize that. Product will say, hey, we don't have time for that, we need to ship our product faster. It doesn't work. So this requirement is very important also. And finally, you need to have the tracing data quickly available. This is important for firefighting in production. If you have an outage in production, the reports, the alerts are coming and saying that this system is slow, you need to have this available immediately to diagnose the problem. So, talking more about application transparency, this is mainly possible with shared libraries. For the people here that do backend development, how many of you use shared libraries to make requests to each service? How many of you? Yeah, that's what I'm seeing right now. I'm actually observing companies that are going with a lot of service, but don't have these shared libraries that they can propagate code. And Google achieved this requirement by propagating instrumentation in 3 parts: in the threading lib, in the control flow lib, and the RPC lib they use. And actually, there's a very interesting phrase in the paper that Google, our instrumentation is restricted to a low enough level in the software stack that even large-scale distributed systems like Google Web Search could be traced without additional notations. That's the importance of this, shared libs, okay? And another interesting number, Google also found that sampling is necessary. You cannot trace everything in production. It will have an impact. I will show you in some slides. So the ratio they found that was good for production is 1 by 1,000. It's not 1% of the traces. And this ratio is enough to provide detailed information of the requests. Okay, so talking more about the how Dapper traces. First of all, there is two ways of tracking requests and tracing requests across service. That is black box. In the black box way, in the paper is not deeply described, but you don't tag a request, don't use an identifier. You just do statistical regression to link all the requests, and this is actually slow. Is a process is slow and is not efficient. Dapper uses a notation-based way that the application or middleware that you have in your code will tag every request and propagate the trace to the end. Okay, it's a global identifier, the trace ID. So basically, in Dapper, for a given request, imagine you are searching cats on Google. You have a tracing tree, okay? And the tracing tree is can be a request on the front end. There is no parent ID, so it's the root node. There is a span ID, that is the ID for that specific request. And then it does requests to the backend that have the parent ID of the front end requests and further. Each node is called a span. They share the same trace ID. That's the way they are linked. And an edge is a dependency, is the requests. Okay? That's just the model of Dapper. It's simple. Okay? So in these requests can be some of them, and you can have clock skew in the timestamps because it's a distributed system. So Google used an interval for the server timestamps. And that's it about RPC span notations. Okay, so as I said, this was possible with shared libs. Near zero intervention from application developers. It was mainly just upgrading a shared lib to new version. And talking more in particular, the threading library. The paper doesn't detail a lot what this does in particular. The architecture, but basically in the thread, the tracing context is injected. Okay, the trace ID, the spans, it's injected on the threading library. And this container is small, so there is no performance penalty, substantial performance penalty of injecting this container. The control flow library, this basically is registering callbacks in a thread pool and then executing later. They also instrumented this library. The callbacks have the context of the traces also. And the simplest library that I've used and drive this kind of approach for propagating IDs is in the RPC framework. Basically, you have a lib to make a request to another service. That lib propagates the trace ID. Another server receives the trace ID and propagates further downstream. Okay? It's simple, just a unique ID for all the requests, okay? Are you following up? Good? Okay. So, annotations. This is useful if you want to add metadata to the trace, okay? You have two types, test annotations and key value. Key value is useful more for making reports on the traces. You will see later that Google developed an API to Dapper and they built some tools on top of it. And this is the key value annotation is useful for that. You can associate a certain feature to requests. You can say, hey, this service is processing a request because of the feature of Google Hangouts or Google Meet, whatever. It's very useful. So, until now I thought about the architecture of tracing, how having global trace ID is important, how Google instrumented. Let's talk about the trace collection, how the process works. Basically, these shared libs write asynchronously to a local log file. Okay, this is completely asynchronous process, and as you can see here, in each production host, there is a Dapper daemon running, and this Dapper daemon, they don't specify in the paper, probably expose a port, and these collectors, they scan every host and they gather those traces, and then they insert in the big table repository. Okay, every row on the table is a trace. Every column is a span, those nodes you've seen before, and this can be sparse because requests can have 1, 2, 3, or 4 spans or more, right? They estimate this latency. No, they actually measure it. The median latency is 15 seconds, but sometimes it can take hours. Okay, depends on the traffic, of course, of the host machines. Okay, so talking about security and privacy. As you saw before, Dapper, we just did with the shared libs, they collect the service that is processing the request. So they, by default, they don't inject the payload on the trace because of security, right? You can have critical data of people, a Gmail user or something. So if you want to annotate that payload, you should use annotations. Okay. And actually, one interesting thing that they describe in the paper is that since with Dapper you can know which services are communicating with each other, you can verify if an isolation policy between two services is being accomplished. They don't detail a lot of this. I never saw these kind of requirements in the companies I've worked, but I expect that this sometimes can happen. Isolation of service and stuff, security. That's another advantage of Dapper. Okay, so talking about the deployment status. First of all, this status is 2 years after Dapper being in production. Okay, we are in 2019, so they may have more insights about this, but mainly, as I said before, the critical parts is the shared libs about trading, RPC, and control flow. Ooh, a type weird. The core instrumentation in C++ is less than 1,000 lines, in Java is 100, 800, and for the key value notations is about 500 lines. The Dapper daemon that you saw here is actually available in every server at Google. So this enables all production applications to be able to be traced. Cool. They also found that the shared libs was not enough, the way they propagate IDs, and they developed a simple library to propagate manually the IDs between requests. Okay. And actually, an interesting number, 90% of Dapper traces contain annotations. So this feature is important for developers. It is actually a contradiction, right? Because they say, hey, we don't want developers to change their code, their application code, but they are using annotations, right? And as I said before, annotations are being used to relate choices with the feature. Yeah, that's a use case of annotations. So, creating and storing the spans, and logging them to this is the most important source of overhead. Okay, but yeah, okay. They measure this time of creating a root span. The first one, it takes about 204 nanoseconds. It's cheap. Non-root spans, it takes less time. 176 nanoseconds. So there's a difference because they don't need to generate a global trace ID. The root span have the global trace ID, they generate this unique ID, and then they propagate. Okay. That's why it's faster. And for annotations, there is a cost of 6 nanoseconds. Fast. No worries. Okay. The write to local disk logs is the most expensive operation, but as I said before, it's asynchronous. No worries about that. Okay. But you have something that you have the Dapper daemon running in every host. And they measure it with unrealistic heavy benchmark, and this daemon uses less than 0.3% of CPU. They actually launched the process with low priority in the kernel. Okay, so the impact on the daemon is also suitable for production. Okay, there is a table here about the. Okay, this table is about sampling. As I said before, sampling is essential for the low overhead of Dapper. And you can see the numbers here. If you have a sampling frequency of 100%, the latency of this benchmark it's on the web search. They don't detail too much. This benchmark, it's increasing by 16%. Okay, and if you start doing 50%, it's 9% of latency change. And then you find the sweet spot of 1 by 1000 sampling ratio. Okay. You can see that. Are you seeing this table? Are you able to read it? Really? Cool. Because last I cannot see it. You have good eyes. Okay. One other thing. Yeah. Another advantage of sampling with a low ratio of sampling is allowing the collection infrastructure to don't have the necessity to collect a lot of logs per time. Okay, it's also good for this infrastructure of collection of logs. But you are seeing here, this ratio is fixed. Okay, so this can work for high traffic service, but with low traffic service, they changed the approach. They basically use another model for sampling, that is the number of traces per time. So, for example, if you have a prototype service in production with low traffic, they say, hey, I want at least 3 traces by second. Okay, it's a different approach they are using. They also are using sampling in the collection infrastructure. Okay, so this is because they measure the amount of data and they were collecting 1 terabyte of trace data per day. So they did sampling in the collection infrastructure as well. So talking about Dapper tools. One thing the Dapper team concluded is that, okay, Dapper is cool, you can trace requests, it's low overhead, but we need to bring more value. So they developed an API that you can search traces by the trace ID. You can also perform map reduce with bulk access. It accepts a function and you process something. And you actually can also find traces by the host name or the service name. Okay. They found that just by the host name, this key was not used. So they create a compound key of host name, service, and timestamp. And they have developed some analytics tools on top of this API also. Another tool they developed is the Dapper User Interface. Another typo here. Basically, on this section, you select the time window, the metric that you want to evaluate. There is a performance summary here, okay, an histogram with all the latencies. In this part, you have an execution pattern, and the service that you are finding the traces is highlighted. And in this section, we have actually traces. Okay, as we have in the Chrome Dev tools for the network requests, it's the same kind of stuff. Okay. yeah, for this user interface, it seems Google doesn't do design well for their internal tools, but it's not about that, right? So, some experiences. There is actually a case study at Google with the Google Ads review system. This system is basically an automatic review system that verifies if a given keyword is inappropriate or something. And from the first prototype, they used Dapper. And this was good for finding those bottlenecks. And they actually find something interesting that was they were making queries to database masters instead of making also to the read nodes replicas. And Dapper showed that in the traces. It's actually interesting. We launch things to production, we don't know what what nodes you are using in the queries. Dapper showed that. They actually found also found the cost of making queries in the dependencies. In the QA process, they also use Dapper for asserting the system behavior and performance. And the thing that for me is most important on this case study is that the ads review team estimated the latency improve 2 times by using Dapper and improving those bottlenecks. That's the end goal of Dapper. And particularly, we see a lot of companies that are growing in the cloud. They don't monitor anything about these requests, and this is very useful. And if you use New Relic, you know this kind of information is useful to improve the system. You can be the best engineer, but without these monitoring tools, you are by your own capacity of thinking about everything at the same time and forgetting a lot of stuff that you left on the implementation. Okay, Dapper was also used for to link traces to exceptions. More stuff. Okay, so long tail latency. There was an engineer that developed a tool that from a lot of traces, from a given set of traces, it inferred the critical path. And they also found three things that he also developed the three requirements. It was the impact of network. The impact of network didn't bring affect a particular system, but was easily propagated in the over latency of requests. He also found the same thing that the Google Ads review team found, that was making unnecessary requests to service. Okay, and he actually built a repository that linked traces with slow queries with examples. Okay, this is very useful, having the examples of the slow queries to improve. Another interesting thing of the usage of Dapper API was inferring services dependencies. How many of you, is anyone of you doing infrastructure? Anyone? Sorry. Okay. So this is actually a normal problem. It's a problem, right? Knowing dependencies, you want to move status from a cluster of Kubernetes or something to another region, and you need to know the dependencies. Actually, someone at Google developed a tool that automatically, for a given service, it gives the dependencies. It's very useful in operations of infrastructure. Okay, lessons learned. Okay. There were some improvements left on Dapper. The first of those improvements was being supports batch requests. Imagine if you batch a lot of requests that write to disk, and then you execute all of them later. This kind of computation doesn't report well on Dapper because only one of the requests will show on the trace. Another lesson learned is that Dapper was created to measure requests from users. Okay, you are searching something at Google, you are viewing your email, that kind of stuff. But this is also useful for offline workloads. You are processing data every night, you are generating reports, and you, in that scenarios, you want to also measure and want to trace everything to find bottlenecks. Another problem they found is that when you have a request that is taking time, sometimes it's not the fault of the request itself, but because the queue of the request is actually big. Imagine a web server that have a lot of requests pending. And this kind of information, this kind of context is not trivial on the Dapper model. So a possible approach was annotate the queue size of requests in the trace. So when someone was inspecting a trace in Dapper, they say, okay, this trace is slow, but the problem is that the queue size is 1000 or whatever. Okay, actually a nice finding in Dapper. And yeah, that's basically the paper. We talk about why Dapper is important, how Dapper collects data, some lessons learned, some case studies. And what I take from this paper is that the cost of implementation was important to the success of Dapper. The shared libs were very important, and they easily could implement Dapper in every application. And showing this, they actually talk about that in the paper, showing that the performance of arrays was low, was important to convince the teams to adopt Dapper. That's the 3 main points I take from this paper. And yeah, that's it about the paper. I would suggest that you investigate Zipkin. That is an implementation of this approach of tracing requests. I've used this at Endive, and actually I was able to improve an endpoint that was taking sometimes 10 seconds to 200 milliseconds with trace data. So this actually works. It is important if you want to optimize these over latency problems, okay? And yeah, that's it. I hope you start tracing your applications, and feel free to question some typos I add here or whatever you want to share. And that's it. Thank you.